Now, let's look at some other principles concerning Newman projections. For instance, we should be able to compare two eclipse structures to each other. For instance, let's say you have this Newman projection right here of a molecule and this Newman projection of another molecule. Now, focus on the left-hand molecule. Notice what's different is that he has a methyl on his front carbon and the molecule on the right has a hydrogen in that location. And let's do this. Let's expand out that methyl. Remember, that carbon would have the 3 hydrogens projecting outward like this. And remember, each one of those hydrogens is in an s orbital. And each one of these orbitals would have electrons in it. Let's create the same orbital view for the molecule on the right. This would be the 2 s orbitals for these hydrogens. Notice in the molecule on the left, you would have increased crowding. This would cause the orbitals to be closer together, which means the electrons in those orbitals would be also closer together. And remember, electrons like to move away from each other, so this would be higher energy. The name of this is called steric strain. We would simply say the molecule on the left has more steric strain than the molecule on the right, and this in turn causes this molecule to be higher energy or less stable, making this molecule on the right lower energy and more stable. We have to remember the effect of steric strain on a conformation. Now, another thing we can do here is compare 2 staggered structures to each other. And in order to do that, let's talk vocabulary here. Let's make some observations. Notice the front carbon for the molecule on the left. He has a methyl group pointing upwards. And the back carbon of this Newman projection also has a methyl right here. From our point of view, these 2 methyls would be 60 degrees apart from each other. In organic chemistry, we call this the dihedral angle. It's simply the angle that a group on a front carbon of a Newman projection would make with a group on a back carbon. Whenever that angle happens to be 60 degrees, we call this a gauche interaction. So, in a sentence, you would say, the methyl on the front carbon is gauche to the methyl on the back carbon. However, look at the molecule on the right. What is the angle made between the methyl on the front carbon and the methyl on this back carbon here? From our point of view, notice they are 180 degrees apart from each other. There's a name for this as well. We would say that these methyls are anti to each other, or they are participating in an anti-interaction. What we need to understand here is that gauche interactions are higher energy, less stable than anti-interactions. But again, let's understand why this is the case. Notice, focusing on the structure on the left here, this methyl, if we were to expand him out, he would look like this. And the methyl on the front carbon, let's expand him out like this. Notice the closeness here of these 2 orbitals around these 2 hydrogens. What we're seeing here is more crowding or more steric strain. And we just learned, remember, that the more steric strain you have, the higher the energy, the less stable. So we're simply seeing that anti-interactions have less steric strain than gauche interactions. In fact, we can take this concept a little farther here. For instance, think about what we just learned. Which one of these molecules would have more steric strain and therefore be higher energy, less stable? Notice the molecule on the left here has a methyl group on the front carbon. And using the vocab here, we would say that that ethyl is gauche to this methyl on the back carbon. The molecule on the right has a gauche interaction, but it happens to be between this methyl right here and this methyl right here. Which one do you think would have more steric crowding? Of course, it would be the molecule on the left. He would be higher energy, less stable than this conformation on the right. So the more bulky the groups are that are participating in a gauche interaction, the more steric strain, the higher the energy, therefore the less stable it is. And at this point, we are now ready to do conformational analysis. And here is a typical problem right here. This one says, give the lowest energy conformation of 2-methylbutane about the C2-C3 bond. Notice the steps that I go through here. The first thing we're going to do is just what we did in the last problem, is generate a Newman projection. And remember, we always start with a rough sketch of the molecule. Here's what it looks like, 2-methylbutane. And we're talking about between the C2 and C3 bond. So this is our carbon 2, this is our carbon 3, making this carbon in the front of our Newman and this carbon in the back of our Newman. So here we go. Here's our front carbon. Remember, we ask ourselves, what are the 3 things directly connected to that front carbon? We got the 2 methyls and the 1 hydrogen. And again, remember, we place those anywhere we want. Let's put the methyl here, another methyl here, and a hydrogen right here. Now, working our way to the back carbon here, remember, he has the 2 H's and he has a methyl. So let's place up our back carbon here. Now remember, we want the lowest energy conformation, so you should place that back carbon in a staggered conformation. Again, because we know staggered is lower energy than eclipsed. But here's where we want to slow down. Think about this for a second. What is the bulkiest group on the back carbon? Of course, that would be the methyl. And look at your Newman projection. Look at that back carbon. Technically, we have 3 options to place that methyl. We could place it on the bond pointing to the upper left, or the bond pointing to the upper right, or the bond pointing straight down. So here's what you would think in your head. You should say, well, if I place the methyl on the back carbon here, then think about what that would give us. Notice this would be a 60-degree angle right here. That's the dihedral, which means we would have a gauche interaction right here. But notice that methyl is also 60 degrees to this methyl on the front carbon. This would be another gauche interaction. So putting the methyl there gives us 2 gauche interactions. Let's see if we can do better. Remember, we want the lowest energy. So instead, let's place the methyl at the second option right here. And let's analyze. Notice what you would have in this case would be 1 gauche interaction right here. But notice that methyl on the back carbon would be anti to the other methyl on the front carbon. So placing the methyl here gives us only 1 gauche interaction. That's going to be lower energy. But just to be sure, we should think about putting the methyl here to see what we would get. And notice what you have here is a 60-degree angle to this methyl on the front, giving us a gauche interaction. So in this conformation, we would also have only 1 gauche interaction. So the question is, where should we place the methyl? Well, in this particular case, you could place it right here as you see, or we could place it on the upper right-hand facing bond. So technically, there's 2 possible answers here. So let's just leave our methyl right here then, which means, again, go back to our rough sketch. We've placed the methyl on the back carbon. Now we have to decide where the 2 hydrogens go. And that's a no-brainer. We would just simply fill in the 2 hydrogens right here. And this becomes an acceptable answer to this question. This would be one of the lowest energy conformations of 2-methylbutane about the C2 and C3 carbons. Now let's look at another conformational analysis problem. This one says, now give the highest energy conformation of 2-methylbutane about C2 and C3. So again, the correct steps that we would go through here is we would generate a rough sketch of the molecule here. Here is our 2-methylbutane, and we want to focus on carbons 2 and 3, so this would be carbon 2 in the front, and carbon 3 right here will be in the back. So we're ready for our Newman projection. Here's our front carbon, and we want to place the 3 items on him, so we look back at our rough sketch, and we notice again, of course, we still have the 2 methyls and the hydrogen, and on the front carbon, remember, we could put them any way we want because we're going to play around with the back carbon to get the highest energy conformation. So looking at the back carbon now, remember he has the 2 hydrogens and the methyl. And now this time we're looking for the highest energy conformation. So we should start out with an eclipsed Newman projection. And let's notice our bonds here on the back carbon. We got this one right here. We got to place something here, and we got to place something here. Now, to get the highest energy, remember we would want the more bulkier groups to be eclipsing each other. So these two bottom bonds, notice the one to the left, lower left that is eclipsing with the methyl, and the one to the right is eclipsing with the hydrogen. And the third bond pointing straight up above on the back carbon is also eclipsing with the methyl. And according to our rough sketch, the most bulkiest group on that back carbon is a methyl. So here's what we'd like to do is make sure that our methyls are eclipsing in this structure, which means you can put it right here if you want, or you could put it on the lower left pointing down bond, which would also give you a methyl-methyl eclipsing. So in this one, we also have a possibility of two acceptable answers. But let's just leave the methyl right here on the back carbon, and now let's place our two hydrogens, and they would go right here. And there it is, that's your answer. This is going to be one of the highest energy conformations of 2-methylbutane, about C2 and C3. Now keep in mind, it takes me longer to walk you through all of this than for you just to do it very quickly on an orgo exam. In fact, that's why you want to practice a lot of these problems so you can get this done quickly. And remember, this is one of the cases where in organic chemistry you're solving for X. Think about this. I'm not getting to this answer simply because I remembered something in my orgo textbook. I'm getting to the answer because I know the series of steps that I need to go through to get to a particular answer, but I am leaning on orgo principles to land on the correct answer. Now, at this point, you might be wondering, why are we doing this? What do we really care what conformation an organic molecule adopts? Well, briefly, let me show you why this is so important. Remember, let's say this is the answer that we got in the previous problem here. And let's do this. Let's convert him back to the other way of representing organic molecules right here on the right. And just to make sure we got everything matched up, remember the Newman projection is looking this way. It's seeing that carbon right there in the front. And our Newman projection happens to have two methyl groups eclipsing at the top. And notice that's exactly what we have here in the structure on the right. Now, let's take this molecule right here and let's pretend for a second that it's a drug that someone could ingest. Remember, we predetermined in that last problem that this happens to be the highest energy conformation of this molecule. And let's say someone ingests this molecule. And one possible fate here is that we have some kind of enzyme that happens to be an integral protein that spans the membrane of some cell within the body. And let's say that particular enzyme has 4 pockets on it, like this. And let's also say that it just so happens that those 4 pockets are a certain size. And that this molecule, in order to activate this enzyme, it has to be in this particular conformation to exactly fit in the enzyme. And when this happens, it activates that enzyme and causes some kind of intracellular processes. This is how the drug is going to take its effect on the body. But what we're seeing here is that the drug could only work if the molecule happens to be in this particular conformation. In other words, it wouldn't activate the enzyme if it were in its, let's say, lowest energy conformation. So think about this. If you are, let's say, a physician and you want to inject this drug into a patient, and you happen to know that this is the necessary conformation, before you inject this drug, would you want to, let's say, put it in a refrigerator and cool it, or would you want to heat it up first? Well, thanks to conformational analysis, since the highest energy conformation is desired, we would heat up the drug before we inject it, because we want to give this drug enough energy to adopt this high energy conformation. If we wanted the low energy conformation, we should put it in the refrigerator first. So notice, conformational analysis is very important. We're not just simply having fun twisting bonds and thinking about all the different types of conformations that a molecule can exist in. Let's look at another sample problem. This one says, draw all the staggered conformations of 2,3-dimethylpentane about C2 and C3. So this time we're not looking for higher or lowest energy structure. We just want to represent all three possible staggereds. And I want to prove to you that as well, is that there is a total of 3 staggereds and technically 3 eclipse Newman projections for every straight chain alkane. So of course we'll start with a rough sketch of our molecule. This happens to be 2,3-dimethylpentane. And we're going to need the room here, so let's scoot him up. The problem is stating about C2 and C3, so let's label that. Here's carbon 2, here's carbon 3, front, back, and in blue we can see these are the 3 items on the front carbon. So let's generate the first Newman projection. Here he is, and remember we could randomly place those 3 items. Let's put the methyl up here, let's put a methyl over here, and a hydrogen right here. Now let's take care of the back carbon. Notice he has a methyl, he's got this ethyl thing here, he's got a hydrogen right here. And now remember, we want all 3 staggered, so let's start out with the back carbon staggered, and let's place our 3 items. And since we're not concerned about energy, we could randomly place them anywhere. So let's put a methyl right here, let's put the ethyl over down here, and let's put that last hydrogen right here. So this is one of his staggered structures. And let's do a little energy analysis just in case here so we could distinguish them. Notice right here you would have a gauche interaction between those 2 methyls. And you would actually have another gauche reaction right here between the methyl on the front carbon and the ethyl on the back carbon. Now let's generate the second Newman projection staggered. Here's what I want you to learn. When you're doing this, keep the front carbon in the same arrangement. Notice, look at my 2 front carbons here of these Newmans. They're exactly the same. And again, draw the back carbon staggered. And what you kind of want to do mentally here is focus on any group of the back carbon of the first Newman projection that you drew. For instance, just by choice, I'm going to pick this methyl right here. And in your head, what you're doing is you're thinking about rotating this back carbon to move the methyl, let's say, to the down position. That means, look at your Newman projection here on the right, the methyl would be now here. And think of the consequence of that. Go back to the first Newman projection. If we did this rotation, then the ethyl on the bottom would move up to the position where the hydrogen is. So that means the ethyl would be here on our Newman projection. And of course, the remaining hydrogen would have to be right here. This can be accomplished extremely quickly in an orgo test. And while we're looking at this, let's do an energy analysis just in case. Notice we have a gauche interaction between this back ethyl and the front methyl. We have another gauche interaction right here between the back ethyl and one of the front methyls. And technically there's another gauche right here as well. Now let's generate one more Newman projection here, and we're going to see that this will be the last one. Again, we place our front carbon in the same arrangement. We put our back carbon nice and staggered. And again, remember how it works. This methyl right here, we're going to rotate now up to this position over here where the ethyl once was. And what that gives us is the methyl is now here. And that causes the ethyl to now move over here. And that moves the hydrogen now down here. Let's do a quick energy analysis just in case. We have a gauche interaction right here. We have another gauche right here. And we have a third gauche right here. Now, here's a key to doing this problem. What I want to prove to you here is that if you were to rotate the methyl one more time, let's say this way, notice you would be back to the first Newman projection that we generated. So that means we've exhausted all of our possible staggereds here. This is number 1, let's say. This would be our second one right here. And this, of course, is our third one. The reason why this is important is because if we're doing a conformational analysis and they're asking us about, let's say, the highest or lowest energy staggered, then you should always aim for the 3 staggered structures, in the sense that you're thinking about these 3. You know that 3 exist, so you know exactly how many structures to investigate to find a lowest or highest energy conformation. As a practice problem, you could try this again, but instead list all the 3 possible eclipse conformations. So this is very key in doing conformational analysis. So what have we learned here? What are our key points? Number one, we saw that Newman projections aid in conformational analysis. We also saw, too, that eclipse conformations are higher energy than staggered conformations due to a concept called hyperconjugation. We also saw, 3, that the more steric strain a conformation has, the less stable it is. And we also saw, 4, that gauche interactions are less stable than anti-interactions. These are the key points we lean on to do conformational analysis.